there is a globally pooled representation available for the clip models, but not for the T5 model inherently is a token based. So they use the encoder of T5. So the final output of that is just token based embeddings. They could pool them for sure, but maybe it's just that like, oh, there's nothing pooled available, or they tried around a bunch of times and found doesn't matter. I don't know.
Okay, thank you.
I recall from the Dream Fusion paper that they tried this and found that there was no real advantage to having all three, and that T5XXL by itself was good enough, and that they didn't need like the tiny marginal gains of doing all three.
Yeah. Although we are like, I think with these models, we are now in the domain of tiny marginal gains largely. But yeah, it's probably, again, that's why I'm not a super big fan of going into all of the details of exactly which schedules they tried out and so on, because it's largely going to be probably some interaction between what data set they have, what hardware they have, and what these pre-trained models are like, and so on. But all of these things I would just chalk up to they may have tried and didn't see a benefit yet, and then let it be.
I mean, honestly, that's just a problem with Stable Diffusion's architecture specifically. You can only do that with high precision, and I don't exactly know why, but there are other diffusion models which you can train low precision as well. I'm not quite sure why Stable Diffusion, like the latent diffusion stuff specifically, somehow has a hard time with floating point errors.
Can you explain what's going on in Figure 2 on the MMDIT block after the layer norms?
So that's on the right hand side here.
Mm-hmm.
So these parts here. Okay, yeah, we didn't dive at all into the right hand side here yet. So maybe that's a good time. So
one more step here. Can you tell us what the modulation does?
Yes, that is just, it also takes this information in here. It's just, I think it's I don't know what kind of layer, but it just also is an opportunity for the global pooled information here to influence the output. So the architecture built upon that only considers class conditions and uses a modulation mechanism to condition the network on both the time step of the diffusion process and a way to incorporate that, but we can maybe go look that up.
I mean, what I find interesting is, so I'm very familiar with those kinds of things because they're used in document analysis all the time. These modulation layers, where, for example, you have like your content, like your actual text you want to generate, and then your handwriting references. You then add the information in with these modulation layers, or usually it's like merged into normalization to adaptive instance norms, but that's just an implementation detail. I find it's interesting that this rather old technique is still like now suddenly crops up in the newest Stable Diffusion stuff.
So I have the paper here, formers. So this is this DIT paper they reference. That's a latent diffusion model of images replacing the commonly used UNet backbone with a transformer that operates on latent patches. And we'll look for so here the time step and the label, they would go in here. That's conditioning information. And I don't particularly find too much else than to suggest that this is just, I would guess it's some sort of MLP.
Usually, you just literally take the activations, scale them, and you add the other one.
Okay, yeah. But you
so
embed the conditioning information first.
So you're saying it's just a affine layer or something?
Effectively, yes, but usually it's even easier because it's not even an affine layer. It's a single scalar that scales it up in a single offset beta. So the way that was used, so maybe they're even doing that, but kind of keyword is adaptive instance normalization. Yeah, I think that you may have it here. If you scroll down, adaptive
so the
instance norm, you
first,
have it.
but I think this is also going to be in the class label as 2 additional tokens in the input sequence, treating them no differently from the image token, similar to the CF time step and so on, just as a sequence token, so they can be attended to. And then there's a cross attention block, and then there is
Adaptive layer norm, or I think they also have adaptive instance norm here. I think I saw it briefly. But yeah, it's the same idea, just that it's
scale and shift parameters. We regress them from the sum of the embedding vectors of T and C. Efficient. So usually in layer norm, you would learn scale and shift parameters. So that's the modulation mechanism, if I understand that correctly.
exactly.
This one. These make a bit more sense now. So there are, I think the important bits are first, you can see there are lots of residual connections as you would expect. As you would expect that. So bypassing all of this stuff, and that's one thing that allows you, even though there is interaction in the middle, that allows you to retain largely the information that comes into these 2 streams. So that's one.
Everything that's outside of the attention block is on a per token basis. So ahead of the attention block and downstream of the attention block is per token.
Correct, as far as I understand. So that these things will be as you would find in a normal transformer block, except that the attention here is cross attention across 2 different token sequences, if you will. And then you can see all of this sidable information about the prompt. This is instead of, so this other paper that we just looked at, they did class conditional embedding or class conditional representation of the prompt that goes here. So this gives global information like a class label, and then the time step. So these together make the Y, and the Y, as you can see, these operations. So here you can see that this AC is then in this mod. So instead of learning scaling parameters in the layer norm itself, so the network could, during training, just choose to ignore the signal coming from Y and just learn regular scale and shift parameters. That's entirely possible, but it could also predict different values for different class labels and for different time steps. I think that's the idea, is that the extra information will be of benefit and will allow the network to adapt its offering in sort of this modulating way, like its operation. We modulate here in a multiplicative fashion, right? So you see, or here, more like a gate or a scalar, or usually comes in the form of single scalars or something like this. So just of up or down scaling entire parts of the network rather than really fine-grained. Let's say if this were to sort of matrix out of it and so on, they don't trust that this carries enough information to be able to do that well. So yeah, I think that's my prediction. They don't say that anywhere, but they rely on this. Yeah.
Yes, they are computed from individual linear layers, but from the same global input. And just to be sure, so we are doing layer norm, meaning that we're normalizing each dimension in the token between all tokens in the sequence, right? And the pooling, this pooled representation,
Why am
I don't know if
understanding
it
here?
has the same number of dimensions or not. So I separate in tokens, right? So we just predict for each channel in tokens its own.
So as far as I understand, they will predict individual numbers. So I didn't find it in this paper specifically, but maybe the other one. Scale and shift parameter for each channel individually.
Usually, yes.
Yeah. So and one is that you learn a global scaling, and then you learn a modulation. They did.
Okay, thank you.
Trying to find this in the other paper, but that's about as much information as they give. They just say in this adaptive layer norm, rather than directly learning dimension-wise, dimension-wise shift and scale parameters, we regress them from the sum of these vectors. So yeah, the way this sounds is they take whatever that side information is, so the addition between time step embedding and prompt embed, predict the modulation parameters here, or the modulation parameters here.
Are you sure it's not just like ordinary linear fitting?
Ordinary?
Yeah. That is, solve a linear matrix equation.
You mean like you just closed form solve?
Yeah, the only issue I can see with what I just described is getting backprop information.
I guess you would have to do it in sort of a checkpointy way.
Right. I don't know. That when you said regression
Exactly, it's
earlier, that's
complicated as fuck.
what I heard, although that's not what you said, was linear regression. Because that's what you're getting. You're getting the scale and bias coefficients for a linear regression at the end of the day. And it would seem like using a efficient convex algorithm would be the way to do it.
It's true, but
yeah, maybe it
learning,
doesn't
so
need to
maybe
be that. A lot of these steps don't need to be that accurate, so it could be MLP.
We resolve this. So let me go back to the
this is Stable Diffusion
the
3.
other
I think.
tapadim.
Okay.
Okay. So down here, this is the ADA LN 0 block. So this here, the adaptive so that, if I understand correctly, is for these two here. These are the shift and scale parameters of the layer norm. That's what they call modulation. And also for these gates going into, or you just multiply the signal, which is essentially a gate or a scaling factor. And yeah, especially this here. So if this here is 0, then it's just all is just the if I interpret and pattern match correctly, then that should map to this ADA LN0 block. So these two gating mechanism is, I think, this thing right here. So they say prior, oh no, blah 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 alpha. We explore a modification of this, which does the same. In addition to regressing on these, which are the layer norm parameters, we also regress dimension-wise scaling parameters alpha that are applied immediately prior to any residual connections within the DIT block. So we initialize the MLP to output the 0 vector for all alpha. This initializes the full DIT block as the identity function. So conceivably, that means they're using an MLP to predict the scaling factor for at least for the ADA LN block, where they use the word regress.
So if that's a linear MLP, then that would make sense.
Yeah.
Okay.
It could be total. It could be linear. Yeah. So, but they use the word regress here too. Yeah. Good. All right. So that's the broad architecture. So there is image information that's treated like an image patch tokenization, so like an image transformer. Then there is text information. The text information goes through many.
We are looking at the other screen, I think.
You're right. You're right. Yeah. So text information, so image information going just through patching, linear layers, and so on, like image transformers, text information, going through many models, trying to retain as much information as possible, notably the T5 model, which is not pre-trained on an image objective. They are concatenating that on the sequence length to the other ones, which is special and serves the purpose that later the attention can be directed either at the T5 part or at the clip part for any given token in the sequence. And
I'm still not 100% clear on why it is that concatenating in the sequence dimension means that it can attend to either one.
because you can, so an attention matrix is going to be, you're going to have some sort of a sequence and some sort of sequence, because this is cross attention. So this is sequence 1, and then sequence 2 will do in the downwards direction, right? So they don't even need to be the same length. So an attention matrix, which you get by multiplying q times k, or whatever. One of them is transposed or so, but who cares?
Oh, I get it. You mean it can attend to any element from either one?
Exactly. So the attention matrix will have per entry in this pairwise table here will have one number. So like the number 2, or so like there will literally be the number 2, which means that this element here attends to this element here. And sequence length, that means these could be the first ones could be the embeddings from clip, and the second ones could be the embeddings from T5. And that means it could be that the same token here in the target sequence attends 2 to the clip embeddings, but attends 8 to the same token, but from the T5 embeddings, which would not be possible if they were stacked in the dimension, in the dimensions, because then you could only just say, well, I attend to this token. And then you would later have to deal with the fact that some of these dimensions are a T5 encoding and some of these dimensions are a clip encoding.
Do we know for how many tokens is so what is the sequence length of the T5 encoding?
Also 77.
Oh, really?
Well, they keep it simple, I guess. Here it says 77 plus 77, so
yeah, but I thought those two 77s were both coming from the 2 clip models.
No, the two clip models, they are concatenated in the dimension So the two clip models will end up in one sequence of 77 tokens with number of dimensions equal to number of clip G dimensions plus number of clip L dimensions.
Now,
So what
I
is
did.
this bottom part in the on the left hand side of the 77 plus 77 tokens? So the right hand side is the T5 XSL. The left hand side is 77 tokens from G14, clip G14,
Yeah.
77 tokens from clip L14, and there's this bottom part.
Yeah,
And I'm sorry if you discussed that earlier, I may be distracted, but
it's
do
literally
we know?
zero. It's
Oh,
just
okay.
it's just padding.
You know, I've thought about that since it was brought up, and it seems to me that that's very interesting, that empty spot, because as these contexts could modify, which is kind of the problem that they're trying to address by having the side channel information, but that block that's all zeros, they can start putting stuff into it. That the layers can start putting stuff into those blocks and actually use those for maybe a abstraction scratch pad or something. I don't think it's useless. I think that's actually doing something as it goes through the layers. That block that's all zeros.
Something like memory.
Right.
Yeah, it's the concept is the same as, yeah, it could be like a bit like
Yeah.
tokens or
The way
pad, yeah.
the way I'm thinking about it, and I don't know if it's the right thinking. So T5 is not trained on images. So T5 is capturing the essence of the text per se, whereas clip is a combination of both text and images. It's co-trained. So I presume that we get the better text representation because we are not looking at the tokens in terms of guidance only of where the image should go, but also to capture the exact sentence or the words that need to be shown. I mean that maybe explains the T5 part of it a little bit better. But this extra space, maybe that once we know the words better, then maybe use this scratch space to expand on the guidance from the image point of view that clip tokens understand and use that, as I think Asterix Cat was saying.
Yeah, I don't think it's quite as clean as that, but I think conceptually it might do something like that. The not quite as clean part is that all those tokens from clip and T5 get all mushed around as it goes through these MMDIT layers. So they're going to change. The whole thing's going to change as that goes through, but maybe not very much. The older models, I think, we're just kind of expecting that more or less that information would get preserved, and the important information would get preserved in it, and it doesn't. It modifies. It wanders off in attention, which is what the side channel is doing. But if you've got the side channel to keep it focused, now you can maybe do some more memory-like things with that text channel that you're passing directly into the MMDIT layers.
I mean, ultimately what you're doing when you pad these with like effectively zeros is you crank up the dimension. So practically you can also think about this like a kernel trick where you say, well, I'm no longer going into like a whatever the two clips together is sized space, but in a 4096 dimensional space. So that alone could make it possible that there are just separations that are not apparent in a lower dimensional space.
To be honest, I actually think you're just overthinking it all.
It's probably they tried it out and it worked.
Now,
Yeah, they're just
Right.
needed.
This thing is not built for interpretability, so it's real hard to say what the heck it's actually doing, and it probably was an experiment, and they said, well, it worked, or they just left it that way.
I mean, they needed to concatenate like two vectors together. One had like a bit of a shorter, the like duct tape in this meme with the broken glass, and then they never touched it again.
Or some smart guy came along and said, hey, we can save a
uh,
bunch of parameters by getting rid of that. Let's get rid of it. They did it, and they said, oh, that didn't work.
Now, I did a Control F for ablation, and I didn't find any. Is there any sort of analysis that I missed about, how much of this improvement, and we started off talking about the improvement to text in these images, is from having essentially the latents from 2 or 3 different models, and how many are from this MMDIT architecture?
So they do. They have at least. They don't call it ablation, but they do at least leave away the T5 embedding. So that's one experiment they do, where they say we train our model with 3 text encoders with an individual dropout rate. Hence, at inference time, we can use an arbitrary subset of all 3 encoders. This offers means for trading off model performance for improved yabba dabba dabba. So it's not an ablation in the sense that they trained with it and they didn't train with it, but more like in a trained model that's trained with dropout among the different models, what influence does the T5 model have? So that's here. The left-hand side is all text encoders, and the right-hand side is without the T5 encoder. And well, I don't know. You be the judge of.
Sure.
What it's like a mix between the images are more generally shitty if you don't provide the model that has been seen 68% or so of the training samples, and between it doesn't seem to pay it too much or as much attention to the prompts.
Sure, thanks.
One thing I found very interesting, and that might just very well be a case where like one part of the company is doing something without the other part knowing, is that they didn't do the improvements that Stable Cascade / Würstchen brought
Hate
to.
this name.
I kind of love it. It's at least it's not an animal for once. It used to be an animal, but
you psychopath.
But so for the people that don't know, the thing that Stable Cascade or Würstchen did is they just cranked up the compression factor. So SDXL and also Stable Diffusion 3 has a compression factor of 8. So effectively they downsample 8 times. While Stable Cascade has a compression factor of...
And how are they compressing it again?
So what you have in these, you have these latent diffusion models. So the latent is some like low dimensional space of a VQ-VAE. And the smaller you make that space, you get something which is 128 by 128, I think. I'm pretty sure that's correct. While if you do Stable Cascade, it's downsampled 42 times. So it's 1024 by 1024.
So by compression, you're meaning bottlenecking.
Yeah. But it's not really only the bottlenecking, but the entire diffusion also happens in a low-dimensional space. So effectively, you exchange like a 128 by 128 dimensional flow into like a 20 by 20 dimensional flow. And obviously, the 20 by 20 dimensional flow is much, much more efficient. And indeed, what Würstchen showed that they can train the same model to a higher quality in like 1/8 the number.
2 models. Like afterward, they like then still need the refiner because like this like high compression model like doesn't really like is nice.
Yeah, I mean, what they are now doing is they have this 2-phase approach where effectively instead of unfolding in one single step, they unfold in like a first stage, which actually takes all the text encoding and stuff like that, and then they have the actual model, but they still have a normal decoder. What Stable Cascade now did is Stable Cascade tried to use this fact that they have a very, very tiny space, and if you run it, you can see that like spelling is almost perfect. Like it's not perfect, but it's on the same level as DALI 3, in my experiences. So I find it interesting that this is something that they didn't explore at all and worked very well for Würstchen. But it might also be the case that just one team was working Cascade and an entire different team was working in SD3 and just didn't know about each other.
It's not simply a matter of more efficiency. It's you're forcing a prior onto the.
These like the compression is always, yeah. So what they are, for example, doing is SDXL does a compression factor of 8, and then they go from 3 dimensions to 16, so SD3. So in the end, you're not really getting that much compression out of it. In Cascade, you get a lot more compression, but still, like 42 tokens, or no, what was it, like 20 times 20 tokens, all of them with a dimension of like 16. That's still a phenomenally large space. Like, I would argue it's barely any compression at all. Like, I think I did a test on, what was it? I think it was Stable Diffusion 1.5 still, where I just tested the compression ratios of taking Stable Diffusion and comparing it to JPEG, and it wasn't that big of a difference, depending on kind of how the qualities you set up and so on. Just because, yeah, it's not that big of a compression factor.
Which is not bad.
I mean, it's not bad, but on the other hand, the JPEG reproduce. Yeah, that's entirely the point. Exactly, that's what I was saying.
Yeah, when you say compression, I think abstraction.
Yeah, and I mean, ultimately, that's also the case in like Cascade. So one of the very nice things is Cascade is very efficient. It's very good at following instructions, and it's very good at writing text. And that's why it's confusing when it takes off like 2 teams working on 2 things independently.
By the way, another thing why I think transformers are better than like CNNs is because they are just so much nicer to shard along GPUs. Like something like tensor parallelism with CNNs is just like a complete pain due to the like CNN kernels, and also like something like pipeline parallelism with like the like old like CNN unit. Like if you only have like 2 pipeline stages and you basically split your unit in the middle, like it's fine. But if you kind of go beyond that, like run at the same speed, so yeah, it's I mean, it's all possible, but it's a lot more painful. And I'm really hyped and happy that they are now that SD3 is now transformer based.
But quadratic memory complexity.
Xmaster, when you say
like model parallelism strategies, one would be a tensor parallelism, where basically the like matmul or like the weights of a like linear layer is basically split across multiple GPUs, and then like they are then just like all reduced like together. This would be basically one parallelism strategy. Another parallelism where you basically shard your model layer wise, and you have the I don't know, like you have a 9-layer model. The first 3 layers are on GPU 0. The layer like 4 to like 6 is on GPU. Not as nice with the unit-based CNN. CNN-based unit.
But
And
the big, like, I don't know, but it also means there's maybe a big breakthrough waiting by
this.
Well, it's if most people will probably go the direction that is easy to do on the current hardware, that means not that many people crappy on or just difficult to do on the current hardware, and there could be a lot more research opportunities there because just not so many people are looking at it.
People actually did that back in the days, like a couple years ago. Like Mesh TensorFlow had like full like CNN like parallelism support.
But it's Mesh TensorFlow.
Yes.
Yeah. So okay, maybe we go on a bit here in the paper. Actually, so there are multiple parts to this paper. I mean, this is the basic architecture, right? So consists of these DIT blocks, which make keep 2 separate streams with residual connections, so retaining as much as they can of that information, but then doing cross it.
The case. because this dot is actually
That's true.
concatenation. So it
Yes,
is not
so
cross
it's not
attention.
cross
Yeah.
attention. Indeed. This is
Yeah, it's
this
just
is self
attention.
attention. Yeah. Okay, that's true. So this
And
is
and then I have a question, and I guess it's not fair to ask to you because but still, does it mean that so they can generate the image by providing, I suppose, in the image stream by providing some Gaussian. So does it mean that the number of tokens is flexible or not? I suppose yes, it can be flexible, right?
the number of
And it would not of tokens representing image patches. I mean,
It's-
obviously it can be flexible. My question is just, will the fact that it is not a cross attention but self attention somehow affect like attention distribution towards the image tokens?
That's, I mean, it's a good point. We'll just assume that this concatenation here means sequence concatenation because odd tokens, but we can
No, it is obviously a sequence concatenation, yes.
concatenate the two sequences. So I think I can't really give an answer to that, but then there is this entire section, and yeah, I have no clue how that's going to affect the exact distribution.
And the second question that I do have is if you return to the image of the architecture. Yeah, so it's just so they're generating a single sequence, right, from attention, and then just apply two different linear blocks to the same token. So essentially, we take a single token, updated, and apply two different linear transforms to it. This is right after attention, I mean.
So what I don't know is whether this here is the same sequence, right? Or whether they split it up in the same way they have concatenated it. Right, so they say, okay, the
Yes.
tokens, you know, essentially if we sequence concatenate, we have, I don't know, 154 tokens from the text, and we have, I don't know, X many tokens. We take the same, some sort of final sequence and put them through here and through here, which would be weird though, because again, the convention is that you kind of keep the number of tokens as you go through, and therefore it would make more
they obviously split it. Okay.
They split it up again.
Yeah, they split it. Okay, thank you.
Yeah, but yes, so there's two directions, like literally from this picture. One is up, and that's kind of the mathy part of the paper. So it's the introduction, but then there is an introduction to kind of the sort of diffusion literature, and as Zigzag mentioned, the loss formulations in terms of flow matching. But I'm not sure we necessarily want to go through that right here, also because I don't have a good tablet here. But essentially, they formulate the problem as mapping a noise distribution to a data distribution, and image in our case, and then this is noise from the normal distribution. So Z is going to be some sort of combination, some sort of, I scale down the image usually it's down, and then I add corresponding noise to that image on top. and the t here, that represents the time step where we're at, such that the boundary 1 and b0 is 0, and vice versa, so that at time step 0 you're at the image, and at time step t, whatever, you're, or 1 if you will, if you go from 0 to 1, you are at a pure normal distributed noise, and then the goal is just to revert that flow. And yeah, usually,
So
but here,
wait a second, the difference between flow matching objectives and these, so between the original diffusion objectives and the flow matching ones, is in flow matching, you don't actually invert it. In flow matching, you quite literally try to get a model which can emulate the noising process. And the fact that you can, the fact that you can get the denoising from it is just from the nature you can affect it. You're always only learning forward.
You're saying you're always only learning forward in the case of flow matching?
Yeah. So what you do is you have some flow, like some noise schedule. That's the at t equals 0. You have your data at t equals 1. You have your noise. And what you're now doing is you learn a function which tries to approximate that forward process. So you can see that in the LCFM equation 8 or LFM equation 7. So you have your UT, which is effectively the noise process, and you try to match the marginals, and you just try to effectively get a heuristic that can tell you kind of how would the flow kind of continue from there on out. And what you can later then do is you can later just solve it backwards in T, because it's a normal like ODE. That's more or less the twist.
I'm not sure that's the same way as the normal diffusion DDPM model does. Just because it's easier to apply the noise as a difference to predict the denoised version on each step.
So it still does this effectively epsilon approach, if you mean that. It's effectively the gradient field from one step to the next. So that's effectively what you are learning. And that's effectively is you. What we don't do is you don't learn it kind of in the backward way, because if you don't have a denoising objective anymore, you have a flow matching objective. So there's no denoising going on anymore. You try to match the flow, and later, effectively once you're done, you have that, because it's an ODE, you can just solve it backward. So effectively, if you have like a y prime of t equals f of t y of t, and you want to figure out like an, I don't know, the initial condition, like they would call it like x of s, you just set your like final condition, like your yt of f, and then you replace kind of, and you know, like your x of 0 in this case is equal to y of t minus s, and you can simplify.
So the way that the inference process here would work is that you use the neural network as the noise predictor inside of an ODE solver.
Effectively, yes. So you just, I can write it down, but the major advantage and the reason we're using flow matching now and no longer the kind of forward diffusion stuff is because it gives you a much more stable objective. Because this flow matching is, first of all, it's much more free, because it turns out it doesn't matter which kind of schedule you choose to kind of represent your you still always get the same objective, which gives you a lot of freedom. So for example, these like latent consistency models or stuff like that, which can sample very, very quickly, they abuse that, but basically just finding nicer trajectories. Exactly. And it's also in general more stable, and it has the advantage that you don't need to do, like, you never have to involve any kind of ODE solver or like solving system at all. It's literally just you have something which you can simulate by effectively noising, and then you directly kind of try to match that simulation with a neural network. So instead of the next time you go, you don't need to go from the image again to the final thing. Instead, you have a neural network simulator. But what you can also do is you can use the fact that an ODE, you can just effectively rewrite the time variable. You can use that to go from noise back to the original image.
So the neural network would it learn a one-step noise? Because as far as I understood it, it would actually learn a t-step noise.
Yeah.
Okay. So the neural network always tries to learn how to go from x0, like the image, to the tth step. Yeah.
Yes.
So can I
Because-
try to ask one more question here? So, in order to solve for any of these, so two things, right? So one is you need to learn the score for every, or a model that can predict the score for t, right? And then once you have that, the single step or reduced steps that we're talking about is learning that function for the bijection and the reverse direction, right? Or from the noise. Well, you still have to do distillation, right? I mean,
No.
you don't learn it without trying to learn the actual mapping.
Oh no, you get that completely for free. Assuming some regularity assumptions on the ODE, which generally we just assume, what you can do is, if you have an equation, I can type in text for voice, if you have an equation like y of t equals f of t, y of t. So kind of at the very general, not f of t, f prime of t. So you have this kind of, just like in the paper, is kind of the initial state. So this would be the backward process. So the backward process, and that is equal to y of t, like y of capital T minus s. So here, notice, this is not an actual like ODE. This is quite literally, this is just kind of the actual function. We don't have access to the actual y, but what we can do is we can now differentiate both sides, and we get x prime of s.
I'm sorry to
equals
interrupt, but I don't. Sorry to interrupt. I don't see anything that you're typing. I don't know if others are seeing, and maybe something wrong with what I'm looking at.
It's a channel
So-
called text for voice.
Just share, but I'm almost done.
There we go.
Thank you.
T minus s. So that's something like this. There might be an error in there, but I think it's correct. So effectively, what you've learned is you've learned this capital F. This is the forward process. And if you want to go for the backward process, so this x process, you have to look for x prime of s, and effectively you just invert the gradient flow. And of course, instead of counting up in time, count down in time, but that's to be expected. So instead of having
That's right.
an
So
ODE,
that is your PF ODE, right? That's what you learn.
so what you learn, your flow matching, is the y prime equals f of t, y of t. So that's where you get kind of
that's right.
forward in time, and you subtract s. So it's exactly the same process as above, just now you walk in the opposite direction. So from t backward. This is the same as looking at the dynamics of x. And if you now go and you kind of continue kind of rewriting, you get to x prime of s equals f of t minus s x of s. Basically, if you have the forward gradient field, you automatically also have the backward gradient field. Because kind of it's just, you count backward in time, and instead of going up the vector field, you go down the vector field. So instead of going plus f, you go minus.
Good, yeah, I was sharing sound, I'm sorry. So
Sorry,
in
yeah.
terms of this, sorry, go ahead. Yeah, good. So then after this, they go into two things they experiment with, and these are. This then results in a giant table of different configurations of what they tried. So this is section 3, and I guess section. No, this is section 3. 3 types. So once you have a t, like a time step, you then ask yourself, okay, what are the a and the b parameters? And you can do, for example, this is just linear interpolation. I don't decrease it, I add something, and that something is given by some function, some normal distribution. Here you can say, okay, I have a cosine schedule, so this is essentially an interpolation, but using sine and cosine, so you sort of go faster in the middle, or something like this, and you can do these latent diffusion LDM, like these are like A and B, and they have a derivation how exactly they arrive at those values in order to preserve the variance of the signal. So this is one set of stuff they try. Now, the second set of stuff they try is the actual time schedule. So, for example, if point, and then this is the target, right? The T specifies how you kind of get there. But this is a bad representation. The two axes is better, right? How do you mix the two? So you can either be fully on the image, or you can be how much of the noise, and the linear schedule would be like, okay, as you decrease. Okay, that's also difficult to do. You have to have both on the same axis here, and then the time here. So the first one would be something like this, and then the second one would be something like this, like a sine and the cosine. Oh, that's more of a sigmoid. So these would be the different schedule, and then the second thing is how do you actually sample these? So just because you have the time, so this is now time here, just because you have a mapping from a time step to a given mixture, like given numbers A and B, like how do you mix image and noise, you are still free to not sample time uniformly. And imagine the situation where these are actually sort of sigmoids. So you start with very little noise, and then somewhere in the middle of your schedule you just quickly add a lot, and after that it's a lot of noise. And then the image, you start here, and then wada bing, you go down. Okay, if you were to, this is a completely legitimate schedule, maybe that works well, but in order to learn this well, you can hopefully see that it makes sense to oversample values of t that are sort of in this middle part right here, because there seems to be a lot of stuff happening here, and there seems to be not that much stuff happening here. So whether or not the schedule is appropriate, like how you derive the numbers A and B for a different time step, is to a degree independent of how you, in a perfect world where you could learn the function perfectly, that second part wouldn't matter at all, right? But in a finite world, you have to choose how to select your training samples, and there it could be important to select stuff more where a lot of change is happening. And even traditionally, as far as I understand, even traditionally, the networks had an easier time to learn the beginning and the end of the schedule rather than the middle. So even if we have a schedule like this at the beginning, you're just more or less at the image distribution itself, and at the end you're more or less at the noise distribution itself. And yet the middle is where you kind of have these mixtures and where it's harder to learn. Important to differentiate between the flow trajectory, which determines how you actually achieve or how you get to the noisy image version given original image, noise, and time step, and then how you sample those time steps. And yeah, they have a bunch of different sampling methods. Again, some, like for example, cosine appears again, a cosine schedule and so on. But what I take from this is they try different stuff, and all of this stuff has some heuristic reasoning of why it could be good. For example, log is normal. One option for a distribution that puts more weight on intermediate steps is the log normal distribution. Okay, so if you take this distribution, you will in fact put weighting function, and that just means the loss is higher for samples that come from those steps. So I just take it as they try a bunch of stuff from a bunch of places, and they make giant tables from it. Even these tables, they say they have 61 different configurations, and they test each on 2 different data sets. And this table only shows like the best performing ones. So here are all the configurations. It starts up here. Different losses. Oh yeah, also different losses, different schedules, and so on. And maybe here we'll actually find the data set.
Picking out any pattern in the comparison of all the different configurations.
They do, yeah. So they have a kind of a conclusion section which we can read. I'm looking now here. Maybe we trained the model on ImageNet and CC12M.
So when you say sampling and oversampling, what you're talking about is how frequently you're taking steps. It's not MCMC type sampling.
It's not how. So maybe you mean how fine-grained we make T?
How large or small you make T at any given value of T and noise?
No, what I mean is, imagine how large you make T at an.
Yeah, I'm trying to understand what you mean by sampling and oversampling here. Sampling, to me, as I understand it, and my understanding is certainly imperfect, you're drawing a conclusion. You say, I want to see what this model would extrapolate to at this time T, and the time steps that I need to use. I need to have a time schedule for that. And that's not exactly sampling. That's, how fine am I making my ODE model approximation? But your understanding is no doubt better than mine. What is it that you're actually talking about there?
You don't need to what's that? Self-deprecate. I think your understanding is super well, and I probably haven't done very clear job. So there are two, I think, different things we could call sampling right here. The second one is something like this, in an abstract sense. Imagine here is a start point, here is an end point, and the trajectory, you're trying to learn sort of trajectories that come from some data set. So you're trying to learn those, right? And I tell you some information about the initial condition here, which is hopefully correlated with the path, right? Otherwise you couldn't learn anything. So you're essentially trying to predict the path from whatever that data point is. And I give you that data point, and I give you a t, the time step that I would like you to output. And that's a continuous number between 0 and 1. So you're essentially learning a smooth trajectory based on some properties of the initial data point. Okay, now that's fine, right? And we have a data set. So you could imagine, hey, let me just get my data set. Here is a point, here is a path, here's another point with other properties, and that has a different path to the goal. So you're just trying to learn these paths. And because neural networks are not super fine outputting entire paths, you're saying, hey, I could take this t and I could put it into the neural network, and the neural network is just going to give me like an XY coordinate of the point in the path. Since there is no, it can be as fine or coarse-grained as you want. But if I now tell you, hey, by the way, observe this fact, it's much easier for the neural network to predict the beginning locations and the end locations, because those will necessarily be like close to the start and end points. It's much harder to predict the middle locations because they have kind of the biggest variance. So what you might want to do is, as you train the neural network, you actually want to input a t that's kind of between 0.3 and 0.6 much more often. So you want to oversample from the dataset, only predicts individual points, and you have to decide how you use the dataset. So that's the second part of that sampling thing I mentioned, is just this. It's the machine learning engineer's decision to oversample a part of a given dataset because they know that part is harder for the neural networks to learn, or harder to predict. That
Okay, let me see if this sounds right then. So when you say sample, you mean instantiations of this Brownian bridge from the start to the end, and because the variance of the middle of the bridge is much more than the ends of the bridge, you want to sample finer times.
And the other type of sampling, that's the first type of sampling, is how do you even construct that bridge in the first place, right? Do you do, and that's the sort of the do you just add noise with some schedule? Do you do this or that, or do you do from the DDPM paper we've looked at previously? They have these schedules of how they trade off image and noise. So that's even how do you even construct these paths, or in general, and that's a different question. So that is those are the two types of kind of sampling. One actually influences the model, and even if
different types of interpolation. Do they ever do this extrapolation kind of interpolation where they look at the direction things are going in and actually go more than that direction?
In this particular paper, I haven't seen that. I think
you know what I mean, the common trick people use in diffusion.
Yeah, they usually do this in like with guidance information. Yeah, I haven't seen it in this paper. So yeah, let's read the table. So you can see the results of the different different schedule flow combinations here. Yada yada. We observe that the rectified flow with a log norm schedule consistently achieves a good rank. It outperforms a rectified flow formulation with a uniform time step sampling. So that, yeah, okay, that's the second part of the sentence. Thus confirms our hypothesis that intermediate time steps are more important. And by more important, they mean harder to learn, and therefore weighting their loss up or oversampling them is advisable. Among the
But this
variants,
this is specifically because the intermediate time steps have higher variance. Is that right?
that's how I interpret it. So they say the RF loss, the rectified flow loss, trains the velocity uniformly on all time steps. Intuitively, however, the resulting velocity prediction target is more difficult for t in the middle, since for t equals 0, the optimal prediction is the mean of the of P1, the noise distribution, I guess, and for T1, the optimal prediction is the mean of P0. In general, changing the distribution over T from the commonly used uniform distribution to a distribution with density high T is equivalent to a weighted loss with these weights. Thus, we aim to give more weight, like intuitively, to say the variance is bigger. That makes sense, because when we displayed visually, then that's what happens. But whether it's actually variance or if you're really close to 0 or 1, you already know what the correct answer is. Or on the other, like, the correct answer is kind of the same for all of the different trajectories, because they're all gonna, if every trajectory starts and ends at the same location, and it's just about what path is taken, right, then the beginning and end are really easy to predict, and the middle is the hardest to predict.
Makes sense.
For the people that are interested, figure 11 in the appendix has a graph of the logit normal distributions that they're looking at.
Very interesting.
So what's the goal? Forgive me here, but what's the goal of them sampling these different paths? They're trying to get a good estimate of the gradient at the termination point.
So the different paths would literally, there's two things. On one hand, they try out different path construction methods, right? Those are different experiments, but within one experiment, the different paths just represent different images being combined with different noises. So that would lead to like a different path through the space of noisy images. So these are literally the training samples.
So maybe that's also part of my fault because I introduced a little bit of confusion. This UT, which you're effectively regressing against. So what you do in this LCFM or LFM, you have your V theta, Z of T, U of TZ. This U of TZ, what this effectively is, or if you look at, what was it, equation 5, for us here, conditional epsilon. What this effectively is you go in your psi, you look backwards, what was the original x, and then you compute the gradient of that one. So effectively, what this ut is the gradient that this psi process would have at time step t. So if you then go and you match it further down, the actual matching that you do is you go and you match the gradient you would want to have at time step t with this v, which is the neural network you actually learn. So quite literally, you have a process which can go from image to noise, and now you learn a function which kind of emulates this process from image to noise. But the special thing here is, and you can see that in the loss, what you're actually kind of marginalizing over is pt of z given epsilon. So the actual thing that you're trying to learn is you're trying to learn the distribution of your latent code z. And that's kind of the actual clue which you're grounding on. So after you are done, you can now generate things according to this distribution z without needing any like real world image samples. So that's the actual effectively generalization that goes on this v. What you're now doing with these time schedules is just, or not with these time schedules, but with these weighting schedules, which you can see in, it doesn't have a number, above section 3 flow trajectories on the right side. So what you can see there is you have these different ways of effectively weighting the terms inside the expectation. So what you can now do is you can weight up certain elements in this CFM. Yannick?
Yes.
Right side of the thing, flow trajectories. Yeah, so this one. So you can see one higher, a little bit higher. Yeah, exactly this one. So this L of W. So L of W, if you see, what you're effectively doing with these W's is you scale which kind of part of the time kind of has what weight. So by going and you set these A's and B's, you set the W, and the W is just a weight on which part of the trajectory has which priority. That's also why every single one of these effectively in the end will give you the same result, because you just weight the different terms. So if you now go and you look at something like rectified flow, effectively what rectified flow is factors t over 1 minus t. So this is this convex combination. So, and that gives you a specific weighting structure. And then EDM gives you a slightly different weighting structure. And the objective that you kind of have is you need to find a weighting structure which minimizes this loss the best, or in the sense that it can model the actual distribution the most faithful. And that is by basically weighting the interesting stuff in your loss higher and down weighting the uninteresting stuff. And it turns out.
I know I'm going to sound dumb, but these paths are over from the image to the noise. That's your A and B point, or are they over a smaller segment?
No, A and B are just functions that are conditioned on t. So it can be anything.
Okay.
Here, for example, in the case of rectified flow, A would be 1 minus t, and B would be t.
All right. So you've got a path going from the image to the noise, and you're making that conditional on the input value of the time step, and you're learning that.
You're not learning that. These A's and B's, these are fixed. They are just, and you can see that on the right with this WT. WT, so you have the strength of each of these. So if you think about this expectation really is a big sum. So how much you weight each individual thing in that sum, that depends on your W, and W depends on B, and lambda, which you can see on the side, on the left above equation 10, also depends on A and B.
Okay, so F, the neural network, is only learning relative step information.
Yeah. What
Got it. Okay.
what they're effectively, so it's not necessarily relative step information. They're learning the gradient at time step t. So that stays the same regardless of how much you weigh this loss term. So if you have like your epsilon theta z of t t minus the true epsilon, that is just you approximate the gradient, or you learn the gradient at time step t. How much you weigh that thing in a loss term, that's entirely arbitrary. You just say, well, some like gradients are more important to get right than others. And how important they are is what you tune with t, or if you tune with w.
So there are, if I understand correctly, there are multiple things going on. Is that right? Exactly. So one is your BT, which is your noise injection schedule in some sense, right? Because your ZT is X0 plus BT. Well, that's an EDM, but it's slightly different over. Oh, it's right above there. So 1 minus T X0 plus T epsilon. So BT is your noise injection. So that goes in as a factor for your sampling. Or if you go a little above Yannick, the equation was there. A little
You're
below. Where
breaking
was
up
that?
for me, but it could also be a me problem.
For me too.
Okay.
Okay, so that's enough.
This is worse.
Wrong
Okay,
brain.
sorry.
So, I mean, yes, in a sense,
The actual noise injection schedule is this BT. But it turns out, and that's kind of the major work done by the continuous normalizing flow or conditional flow matching people, is that they realized that regardless of how you set your A and your B, in the end you're getting the same thing if you are at the global optimum. Because this A and this B, so this actual noise schedule, the only thing it ultimately changes is how much priority is put on what part of the actual trajectory. So you can kind of think about this as if your A, let's make an extreme case, your A stays at 0 for kind of the first half of the trajectory, and then it's B. So, in the second half. So what you would do now is you would effectively give 50% of the weight of the gradient approximation thing, you would set on the 0 case, and 100% and the other 50% on the 1 case, but nothing in between. And if you smooth that out, you get a much more uniform kind of schedule that they did. There you can see that they say effectively the entire like beginning and end are not as important, like of course depending on which one they actually choose. And then, for example, the red one that gives a huge priority to the T's, which are in between like 0.4 and 0.6. So most of the
wait here now for a second. Because before we were talking about the W, and now we're talking about the